Come here. Hey, buddy. If you have ever wanted to be a STEM professional, engineer, scientist, mathematician, if you have ever wanted to work in technology, if you've ever wanted to be an economist or get into finance, but you are afraid of the calculus series, you're not sure, math has been difficult, and you're not sure looking at that schedule if you can make it, I'm here to say two things. One is you absolutely can. You can make it. I promise you. You're not stupid. There's nothing wrong with you. Most people's experience of mathematics is subpar in compulsory schooling because of the way it's taught. Holding no one at fault, I'll leave it at that for now. There are ways to conceptualize mathematics that are much easier for the mind to grasp. And that's the second thing I want to show you, is that there are mental math patterns that can make all the difference. And not just with arithmetic, not just to be math tricks, but ways of conceptualizing mathematics all the way through algebra, calculus, linear algebra. A slight shift in your thinking can have extremely dramatic results. And there is a mathematician named Ted Courant. He was nice enough to help me out in my early days here on TikTok, giving me some advice on my trig videos, no cost. He just offered free advice. I thought that was pretty awesome of him. And he said something on LinkedIn that really struck me. He said, well, calculus is mostly algebra with calculus layered on top. And I have found that students I've helped, if they're struggling getting into calculus and performing well, it's exactly that. It's that there are missing pieces in their algebra journey. And it's not necessarily that these topics weren't covered by the textbook, but the student had the procedural knowledge, like they were following a recipe in a given chapter, but they didn't deeply understand. They didn't clearly understand what was going on. So in this video, I want to show you a way of looking at quadratics, a way of conceptualizing the structure of a quadratic and what's going on that will make all the difference in the world for you. Okay, factoring quadratics and polynomials in general, very easy with this method. You don't have to come up with a big factor table and all that. And an alternative to the quadratic equation, because the quadratic equation might be the most dreaded equation in compulsory schooling. I've never seen so many eyes roll. And there's a slight shift you can make to it, an alternative that makes it very easy to do. I don't know how, this has been out since the 60s at least, so I don't know how this hasn't spread around more easily. But in today's video, I hope to earn your confidence and to open your mind to the possibility. I want you, after this video, to be able to look at your future through the lens of possibility. What if you could have that career you wanted? What if you could contribute meaningfully to science, to technology, to engineering, whatever you want, whatever resonates with you? I am here, as far as the math is concerned, I'm here to show you the fact that you were born a math genius, and all you have to do to unlock it is make a few shifts in your thinking, okay? And one tiny step at a time, that's how I like to do everything. We're going to, one small step at a time. I think that's the wise way to tackle a big endeavor. We are going to look at quadratics. So let's go to the board. I'll show you what I'm talking about. All right, so there are really 7 steps, 7 small steps to making quadratics easy to deal with. Step 1 is understanding the structure. So there's really no difference between arithmetic and algebra in this sense. Structurally, they're identical. It's just one uses 10 as the base and the other uses a variable. And here's what I mean by that. If I have something like 12 times 13, if you've ever seen an abacus, you know it'll separate out. You have all these rods and little beads you put back and forth. This could be thought of like 10 plus 2 and 10 plus 3. And this is something like making an abacus on the paper, because I've separated my orders of magnitude. Here, I would have, if I want to count this 12, 13 times, I can go in this pattern vertically and crosswise. I count the biggest order of magnitude first, and then slowly descend down to the smallest order of magnitude. So 10 tens are 100, 10 threes are 30. Notice I've multiplied the 10 by the 10 and the 3 out of this 13. And this creates a ratio. These are in ratio 10 to 3, right? Imagine that, because that's what I multiplied by. Well, what that means is when I move over to the units, these pieces of the puzzle will also be in ratio 10 to 3 because that's what I'm multiplying the units by. And here's what I mean by that. I've counted 10 10 times and 10 3 times. Now I need to count 2 10 times and 2 3 times. So 10 counted 2 times is 20, and 2 counted 3 times is 6. Notice these divided by that 2 are also in ratio 10 to 3. It matches. And this is the structure of quadratics. There is no difference once I introduce an x as a variable, because I can treat x like my base. So this structure is the first thing to understand. What if I said x plus 2 and x plus 3? You see, structurally it is exactly the same thing. Here I have x times x, in this vertical pattern would be x squared, which is what 100 is to 10, right? That's 10 squared. Then I would have 3x. And notice these are in ratio. Whenever I have x by itself, remember there's always an implied coefficient of 1 because I'm counting 1x, just like 10 is 110. So this is in ratio 1 to 3. My coefficient is 1 here, and there are 3 x's here. Now, over here, Nala is playing with her cat curls. I have 2x plus 6. And notice this also is in ratio 1 to 3. Now, another way to visualize this, my mic's still working, yes, is to draw a box. Because when we say quadratic, the word quad, meaning 4, from some Latin root, means 4 sides. That's kind of a crooked one, but we'll just go with it. If I have x plus 3 and x plus 4, you can imagine this area would be x squared. Here I would have 3x. Here I would have 4x, and here I would have 12. Well, notice something else. This box model is often taught, but what I do not see often taught is the ratio. If I were to call this x plus 4 times x plus 3, notice the top number, the first number, controls the ratio top to bottom. This is x to 4. These are in ratio 1 to 4. The bottom number controls the ratio left to right. These are in ratio 1 to 3. And if I know that, then factoring becomes much, much easier. Let me show you. So the second piece of the puzzle is factoring. And now that I understand the ratios and the vertically and crosswise pattern that keeps in mind the orders of magnitude, you see if x is our base, we're moving in orders of magnitude, one step down each time. You could think of this structurally exactly the same as 100 plus 10 plus 1, right? X is being multiplied by each power above it. X to the 1th, x to squared, x to the 0th, and so on. So, what am I doing when I factor to make it simple? Well, one thing I'm doing, we call this the general quadratic, right? ax squared plus bx plus c. This is the general form. You can plug in any number for a, b, and c here. What I do typically is I multiply my a coefficient by the c. So a times c here is 12. And then I make a list of factors that multiply to 12 and that might add up to 7. But I want you to think about this a little bit differently. What I want you to do is I want you to split the 7 into 2 pieces of the puzzle that keep the ratio equal on both sides, just like we were talking about. The ratio has to stay consistent. And so if I know that this is going to split into 2 pieces of the puzzle that keep a ratio, well, the coefficient here is 1. This is 12. What 2 pieces of the puzzle could I split that would keep a ratio of something to 12 and 1 to something? Well, of course, that must be 3 and 4. And it becomes even more obvious if I think about what the factors of 12 are, right? There are only so many factors of 12. 6 and 2, 12 and 1, 3 and 4. So when I go to 3 and 4, notice these are in ratio 1 to 3, and these are in ratio 1 to 3. And if I know that, then I know x plus 3, this ratio, at its most basic form, its most simplified form, must be one of my factors. Now, once I've identified one of the factors, I could switch these. Because notice what happens. If I put a 4 here and a 3 here, or excuse me, I just did it there. I just did it exactly the same way. If I put a 4 here and if I put a 3 here, now these are in ratio 1 to 4. And if that ratio holds, I know that must be my other factor. And sure enough, right, if I multiply these two, I have x squared plus 7x plus 12. But suppose the ratio didn't hold, or suppose it was a little more of a complex problem. All I have to do, once I have one of these factors, I can simply use algebraic division to divide it out. Now, if you're not familiar with the easy way to divide algebraically, what we call flag division, that's a video for another That's a video for another time. Comment flag division on this video, and I'll show you what that's all about. But for right now, I want to move on to the next piece of the puzzle for quadratics. And actually, no, I'm not going to resist the temptation. I am going to demonstrate this. If we identified x plus 3 as one of our factors, the way I teach algebraic division in this kind of context, we transpose a negative 3 from our flag. This is not an exponent. This is what's called the flag. X plus 3, I transpose a negative 3. There's one digit on the flag, so I mark off 1 over for my remainder. And now I simply divide. X squared divided by x is x. And I multiply the coefficient of the most recent answer with my transpose flag, and I simply add it onto the next term. So 1 times negative 3 is negative 3. Add it onto this next term would be 4. To get my remainder, I say 4 times negative 3 is negative 12. When I add that to the next term, the remainder is 0, which means this divides perfectly evenly. If that seems like what in the heck is going on or like voodoo, it really is that simple, very easy to do mentally, but maybe requires another lesson. In my actual course, this is part of another week where we look at algebraic division, but I just wanted to show you how useful a tool it is and how easy it is to do mentally. So now, moving on to the next piece for quadratics. All right, here we talk about the discriminant. The next piece of the puzzle is the discriminant. And if this is our general quadratic, ax squared plus bx plus c, the discriminant is this piece of the puzzle. I take b, I square it, and I subtract 4 times ac. A here and c here. Now what this tells me, this gives me information about the roots of this quadratic. The roots meaning, if this is the area, the roots are the sides that make it up. Now, what I want you to think about when you see the discriminant is a dolphin. So I'm going to draw a very simple waves on the ocean, and I want you to think about a dolphin breaching the surface, right? Happy dolphin breaching the surface. When a dolphin jumps up out of the water, it would leave the water at one point, and it would fly up high into the air. Thank you, Nala, for adding sound effects to our video, and splash down on the other side. So up here and down here, meaning it crosses the horizon at 2 points. Now, why do I want you thinking of that? This gives me information about the nature of the roots. If I work out this value and the discriminant is greater than 0, D for discriminant or D for dolphin, right? Pretty convenient. If it's greater than 0, the dolphin leaps out of the water. It's very happy. It's going greater than 0, and it will cross the water, splash in the ocean at 2 points. And so there are 2 real roots. 2 real roots. If the discriminant is equal to 0, in other words, if the dolphin is just poking his nose, his little bottle nose, out of the water, it has exactly 1 real root. And if the discriminant is less than 0, the dolphin is hanging out here beneath the surface, and there are no real roots. Imaginary numbers only. So that's what the discriminant tells you. And I would argue when you have a quadratic and you have to solve using the quadratic equation, this is the piece of the puzzle you want to focus on first, especially on a multiple choice timed test, because when you have to see what are the roots of this, if you can figure out how many real roots there are first step, you may be able to eliminate a lot of the junk answers. Also, it just makes this easier to do mentally because the next piece of the puzzle is the differential, which we will focus on now. Now, if this should be 4. I think really it should be 5. I think I skipped a number, but oh well. So if this is our general quadratic, then the differential or the derivative is the next piece of the puzzle. And here's how I generate it. I work left to right, and there's a little pattern I follow. I take the exponent and I multiply it by the coefficient of x. So in this case, 2a. And then I take the x term and I reduce the exponent by 1. I subtract 1 out of here. So x to the first power is just x. And then I do that the same thing with the next term. Now, because there's an implied 1 here above the x, the formula would be 1 times b, which is b. And then if I reduce this 1 by 1, so x to the 0th, well, anything to the 0th power is just 1. So this remains the same. Now, if I have c to the 0th power and I multiply 0 times this coefficient, that knocks it out completely, right? There is no term. So this drops away into nothingness. And this is what I have left. Now, why am I performing this strange pattern? Well, the reason why that's true is actually for another video. It comes from calculus, differential calculus. But when it comes to quadratics at the college algebra level, if you can find the first derivative, which is what this is, in this general form, all you do, you take the exponent, multiply by the coefficient, and then drop the exponent by 1. Do that for each term left to right. This is the first derivative, the differential. This piece of the puzzle tells me another very valuable piece of information about my curve, which is what a quadratic represents, right? X squared plus 7x plus 12 may, well, actually, this might not look like that at all on a graph. But anyway, let's just, this is an example of a quadratic. This is an example of a curve, which a quadratic represents on a graph. Not the same thing. So, not the exact same thing in this case. But what I'm trying to get at is, what the differential gives me is the slope of what we call the tangent line, the line that just kisses it at is an infinitely tiny point. Now, why is that useful? Because that gives me the rate of change for the curve. We're all familiar in algebra with the idea of the slope, right? If there's this line and it starts here at the origin and it moves like over 1, up 1, over 1, up 1, you say the slope is 1. 1 over 1. It's changing at a rate of 1 up, 1 over. Well, the problem is, how do I find the slope of a curve, of something not a straight line? Well, Archimedes came up with a brilliant way to solve that problem. He cut a circle into straight lines, which made this sort of pizza pie. Now you can see, this is not quite a parallelogram, but it almost is. It just got this like pizza crust bend, complicating the issue. But these lines are straight in the middle. Well, what if you cut the pieces smaller? What if you had 8 pieces instead of 4? Well, now we're getting somewhere, right? Now this looks much more like, I don't even know if that's 8 pieces, but now this looks much more like a parallelogram or a rectangle. And it turns out, if you cut infinitely many small pieces, at infinity, it actually approaches a rectangle whose dimensions are, you can imagine the pizza crust for the top and bottom. So this line is the entire circumference of the circle split into 2 pieces, c over 2. And then this line right here is the radius from the center out. So if I multiply the radius by the circumference cut into 2, as it approaches infinity, it behaves like a rectangle. Well, you can use that same logic with a curve. You can cut the curve into infinitely tiny pieces. And practically what that ends up being is the slope of the line that touches it at an infinitely small point. We are still recording, okay. So, now that I have my derivative, and I have my discriminant, I can solve quadratic equations with relative ease and do it mentally. So let's say I want to solve a quadratic, right? I have here, first I find my discriminant. If this is ax squared plus bx plus c, my discriminant, remember, is b squared minus 4ac. Well, b squared is 49 minus a times c. So you figure 6 times minus 20. Well, 6 times 20 is 120. minus 120 times 4. Well, anytime I want to multiply something by 4, I just double it twice. See, 1, 2, and 4. 2 is double 1, 4 is double 2. So if this is 1 120, 2 120s are 240, 4 120s would just be double that, 480. So A times C is 120, times 4 is 480, and it's a negative 480, so instead of subtracting, because our formula says subtract, when you subtract a negative, it turns into a positive. So here, I would have, you can imagine, like this is much easier to see. So here, I have 52, and then I have 9. So 529 is my discriminant. And if 529 is my discriminant, that's greater than 0, so I know there are 2 real roots to this. Now, my alternative to the quadratic equation is very simple. I simply set my differential to ax plus b equal to plus or minus the square root of my discriminant, which I already worked out, which was 529. Now, what is the square root of 529? This piece of the puzzle is for another video, but you can find square roots very easy mentally. I organize pairs of numbers from the left of the decimal. However many pairs of numbers, 2-digit numbers there are, that's how many digits there are in my root. What number gets me 5 or close to 5 when I square it? Well, that must be 2. Remainder 1. Then I double 2 for 4, and that becomes my divisor. 4 into 12 is 3. And 3 squared is 9. So I can check my work. I can check my work with vertically and crosswise very easily. 4. 6 and 6 is 12. And 3 times 3 is 9. So 529. Yeah, that works out. So when I take the square root of my discriminant, that's 23. And so what my equation is going to become is either plus or minus 23 on this side. And then the left side is just going to be the differential. Well, 2ax plus b, 2 times 6 is 12 times x, and b is 7. So there are 2 possibilities here. I have 12x plus 7 equals 23, or 12x plus 7 equals negative 23. And I can just use transpose and apply to solve. Subtract 7 out of here. And if you're not used to the mental addition and subtraction, one easy shortcut is to treat this like 10, because it's only 3 away from 10. If I subtract 10 out of here, that's 13, and I give 3 back, because this was 3 away from 10. So this becomes 16 over 12. You can imagine if I divide 4 out of that, it becomes 4 over 3. So 4 over 3 is one of my x's. And then here, if I subtract 7 out of negative 23, it becomes negative 30. And negative 30 over 12 equals my x. You could divide a 6 out of this and make it negative 5 over 2. And those are my roots. And so instead of having to deal with the quadratic equation, which I think is very unbalanced, I just set the square root of my discriminant, plus or minus, equal to the differential. And then it's very easy to solve. So if you made it this far, you either really like cats or you're invested in your math education. And if you enjoyed this way of approaching it, of breaking things down into pieces that are easy to do mentally, if you're curious about some of the techniques I showed that I did not have time to really elaborate on, if you want to be some kind of professional, if you want to do something with your life that involves math, but you've always been scared of math, I promise you, you don't need a calculator. You can learn math through the calculus series and beyond easily in a fun way. I've organized a course. It's a 7-week transformation. I only have 5 spots available. I'm only going to work with 5 students at a time for right now as I develop this thing, but it's 7 weeks and it uses 5 to 10 minute daily lessons that break things down into very small pieces. I think you have to do that if you want to master things well. And it will take you through all of the skills needed to master mental algebra and trigonometry to prepare for calculus. So if that sounds like something you're interested in, if you want to open that door in your life, comment What's a good word for this one? Open door. Comment open door on this video, and I will connect with you and tell you how we might get started if you're a good fit. I can tell you right now, I have a screening process, and this course is not for everyone because I need to know you're serious. I need to know you're invested. I have tried to sell lower price courses, doing people favors. I've tried to make it for everyone, and that's been a mistake. I can show you at some point. I'll do a video on this, but I can show you screenshots that people buy the course at a cheap price and they never watch a single video. That's like 95% of people buy the thing and they don't do anything with it. And that breaks my heart because I've been developing my method of teaching, my method of navigating math since 2010 now. And I'm really proud of it. I really believe in it. And I know it can change lives in the right hands. So I'm very careful about who I share it with anymore. I need to know you're invested. So if that's you, though, if you are serious, if you want to be a physicist, an engineer, an economist, get into finance, but that calculus series is what's scaring you, comment open door on this video. Let's connect. I want to help you. Okay. Thank you so much for your time. I know you could spend it anywhere scrolling, and I will see you on the next video.